Good morning and good afternoon and good evening, everyone. Welcome to QCS. I'm Anyab Zhang from Yonsei University, and today I am the moderator for the today sessions. Today's sessions is being recorded, and please keep your microphone off while the speaker is presenting. Hold all questions until the Q&A at the end, and but you can feel free to type in the chat in the Zoom chat. I read those questions aloud, and okay, now it's speakers introductions. It's my really pleasure to introduce our speaker today, Professor Yipeng Huang, and Professor Yipeng Huang is an assistant professor of computer science at Rutgers University, and his teaching and research are in quantum computer architecture. He is interested in the quantum computing applications in simulation and communications, approaches to fault-tolerant quantum computing using reconfigurable codes and high-dimensional states, and more broadly, unconventional accelerator architectures. I'm really happy to participate, Professor Ipong, because a few months ago I finished my 1 year visiting scholar at Rutgers University, and Professor Ipong and me have a really nice and lovely times in my visiting scholar period. Okay. Please join me in welcoming Professor Yipeng Huang, and yes, please start the presentation. Thank you.
Great. Thanks, Senhyo, for the really nice introduction. Um, so today I'm talking about some recent and ongoing work on asking this question of when might useful quantum computing come to exist. Specifically, I'm looking at useful quantum computing in the context of a really difficult benchmark in quantum chemistry. This is Hamiltonian simulation using a quantum computer to simulate quantum mechanics. I'm going to focus on several things. So in this type of question, the subfield has kind of had this journey from discovering how to do so to improving those techniques, and then coming to this realization that in the NISQ era of quantum computing, it's likely that bare hardware quantum computing will never be able to solve this benchmark directly. The hardware needs to be 1,000 times more accurate in our estimates to reach the right level of accuracy. And then, so what we'll do is we'll discuss kind of new concepts of what does it mean for the algorithm to no longer focus on running on bare metal hardware, but instead where the algorithm runs on a quantum error correction code. So I'm trying to introduce this concept, this nomenclature of code efficient ansatzes, where the algorithm ansatz is tailored to run well on the particular code system, QECC, quantum error correction code system. And this looks different when you think about it in far future fault-tolerant quantum computers with very large codes versus relatively near-term small-scale codes. What does it mean to run ansatzes on those? There's this important kind of transformation in how we think about running quantum computers, going from running on hardware to running on codes, which is now the compilation is a matter of going from the algorithm to logical qubits, and from logical qubits to the physical qubits of the code, and from physical qubits to the bare hardware qubits. And after our estimation, we consider that after this correct mapping, the level of accuracy needed for within the code is only 33 times more accurate compared to the 1,000 times that raw hardware needed to be. So that's the overall outline of today's talk. That's basically the overall message. So let's go ahead and jump in and talk about what is this benchmark that I'm interested in. Um, so those of us who got fascinated in quantum computing likely heard first about these exponential speedups in factoring numbers via Shor's algorithm. The other important category of algorithms in the conventional quantum literature is Grover's algorithms for search. But in the near-term era, people realized that probably some of the likely candidates for using quantum computers in an early stage is in optimization and in using quantum computers to simulate quantum mechanics, oftentimes in the form of molecules, right? So molecules are quantum mechanical systems, and it makes sense for a quantum computer to study them. If you have a molecule, it has n electron orbitals, then there will be on the order of n such electrons occupying those orbitals. That's the quantum mechanical system that we're trying to study. But because of the kind of combinatorial combination of all the ways that those electrons can fit in orbitals, if you try to model this problem using classical computing, then you will need a exponential number of bits relative to the number of electrons that you're studying to study that quantum mechanical system. But on a quantum computer, you only need polynomial number of bits relative to the size of the molecule. And so the types of problems that are now being able to studied are on the orders of tens of such electrons, bordering on 100, order of 100. And it doesn't need to be a tremendous number of qubits before very interesting um, molecule dynamics can be studied. So things like catalysis and also protein folding, these are all candidate problems where if the quantum computer can simulate the properties of these molecules, determine the ground state, determine the geometry of the molecule, then that would have significant impact on science and engineering. Um, this talk kind of fast forwards through the mapping, exact mapping of how this problem becomes a quantum computer problem, but there are excellent tutorial and compendium articles such as this one that will teach you about this mapping. What we'll focus on today is a particular strategy, zooming in, where the key idea is we're using these ansatzes. You can think of them as neural networks, where as you train the neural network and execute these neural networks, these ansatzes in quantum computers, we can optimize for the ground state energy of the ansatz, which represents the ground state energy of a molecule. And if you know the ground state energy of a molecule, then you can predict exactly what is the geometry of that molecular system. This strategy, using such an ansatz, such a neural network, is called the VQE, variational quantum eigensolver strategy. The way that this approach works is you take your problem, you propose some kind of network that imitates the ground state energy of your molecule. Uh, in the ansatz, you have all these parameters, which you try to optimize. You simulate the ansatz in a quantum computer that determines a ground state energy of that particular set of parameters. Feed that into a classical optimizer, which tunes the rotation angles to continuously decrease the expectation value, the ground state energy. And once that is minimized, then you have an estimate of the ground state energy of the molecule. This figure is work that is done by Enhyok's colleague, Seungwoo Choi, also a Yonsei University PhD student. And this is work that is ongoing, being done on Seungwoo's exchange student time here at Rutgers University. A lot of the figures in this talk will be coming from this recent work. Um, So let me tell you a little bit more about the chemistry problem, and why I say that this is a challenging problem to benchmark when quantum computing becomes useful. And so one thing I want to show you right now is what does it mean? Why is it useful to determine the ground state energy? So you can, as you see here, I have the ground state energy of a molecule plotted versus different candidate geometries of the molecule. Um, and the molecule has several different energy levels. The ground state has some global minima. And if you're able to find this global minima of what the ground state is, then that tells you that the ground state energy of the molecule is minimized at that value. And that value tells you how far apart these two hydrogen atoms want to be in order to minimize the ground state of the whole molecule. And so knowing exactly where this minima is important for predicting the geometry of a molecule. How accurately do you need to know this ground state energy, capital E? And the way this works is that the reaction rates of different molecular species is related to the exponential of the ground state energy. And so knowing this value to um, within a certain level we call chemical accuracy is able to predict reaction rates within one order of magnitude. And this is kind of the threshold that we declare, okay, the quantum computer is able to simulate this system accurate enough to do useful dynamics prediction. Let's visualize this, right? So this chemical accuracy value is 1.6 thousandth of a Hartree, which translates to about 4/1000ths of this unit here. This is the same unit being used in this plot. And so as you can see, 1/1000th versus the scale of this plot here, really the error bars that you're allowed to have versus uh, the scale that this plot is being shown here, the error bars don't even show up at all, right? So this is to give you a sense of the challengingness, the extent to that this is a challenging accuracy problem. Uh, the mapping of these problems from the original problem to the VQE formulation, this has gone through many generations of trial and error, optimism and dismay. Initially, people had these things called chemically accurate ansatzes, which take the original problem, map them into quantum circuits. That became updated in a couple different generations, one called hardware efficient ansatzes, where we realized that we want to execute the ansatzes in a way that maps to hardware efficiently. And so what you do is you take the geometry of your hardware, the connectivity of your hardware, and try to use that as an ansatz, right? This had some excitement 10 years ago. Quickly, people realized that this intuitive approach does not work and that the ansatz become untrainable, which led to subsequent very successful work in these things called gradient maximizing ansatzes, where you construct your ansatz in a way that ensures the network is as trainable as possible. Um, and so the next few slides is about telling you the story of several generations of ansatzes. And then finally, my proposal, my kind of contribution, or the thing I want to bring into existence, which is this notion of code efficient ansatzes, ansatzes that are constructed to be efficient in a quantum error correction code. All of this is to answer our title question, right? How much farther does it take for us to potentially have the minimum claim that useful quantum computing is taking place for chemistry? Okay, I'll take a pause here. I'm happy to take questions during the talk. But otherwise, our next step is to launch into discussing the first generation of ansatzes. But otherwise, happy to take questions while in the chat too, right? So if you have questions that pop up in your mind while we go, feel
Can
free
you
to
ask
type that in the chat.
questions now?
Yes, Malik, you have a question?
This is Saif. I'm a researcher in content algorithms. I have a very basic question. So, I don't know, have we reached there in this chat or not, but is it really related, this ansatz, choosing an ansatz, is it really related to the problem of the domain knowledge, or is it related to quantum error correction? I mean, do you have to be a chemistry expert to have a good ansatz, or you have to be a good computer scientist or quantum error correction expert to have good ansatz? Uh,
Yeah, so I'll
I
answer that
think I
question
don't
there,
understand.
right? So the answer is to fully understand what the problem is, you need to read about the mapping from quantum chemistry to quantum computers. Ansatzes are a different kind of art form in the form that in the sense that um, there are different choices on the ansatz that make them suitable for a problem or not. And then kind of the newest direction now is that uh, quantum algorithms and ansatzes are no longer going to be executed on quantum hardware directly, but rather instead they will be executed on a extra layer of protection called quantum error correction codes. So let me tell you the first part, right? So this is tending toward the chemistry problem and what makes a ansatz suitable for execution or not. The starting point that we'll take from this talk specifically is we're going to start with the DNA of a molecule. So this is the outcome from a several stage translation going from the molecule's energy description through different forms of discretization in terms of the orbitals, in terms of electron occupancy, in terms of uh, operators that place electrons and take electrons out of certain orbitals, and exactly how you translate that into something that is a quantum circuit. Um, what we arrive after some sequence of these translations is this DNA, right? This is called a polystring, representing the molecule. It's called poly because it consists of these poly bases of quantum computing, and there are several sequences, several strings of this alphabet put together. And given this DNA of the molecule, everybody's first idea in the subfield was to, okay, let's take these strings and turn them into ansatzes, where you take each component of the Hamiltonian, you take each string, and you create a parameter that allows you to tune the weight of that given string, right? And so you go through the sequence of all these strings, you iterate through the strings. Each string becomes a poly block. The way that a poly block gets mapped is you take the letter and you rotate the specific qubit into the basis that matches that string. You entangle the relevant qubits together using this ladder of CNOT gates, and then you rotate once inside that string, and you iterate through the whole sequence of strings, right? This is called, just to link this to the terminology, this would be showing up in the literature called UCCSD, unitary coupled single doubles ansatz. And in work done by our research group at Rutgers, by my PhD student Zirui and PhD student Yue Jin. In recent work, we observe this and we say, look, there are opportunities for optimization here. Opportunities for optimization is the particular order of that these strings show up does not matter, right? You can tackle different orders of strings at once, and you can optimize the ordering of those strings such that between strings and strings, you have these opportunities for gates to cancel each other out, thereby decreasing the number of gates that you have to execute. And we explored this idea in 2024, published in this paper called Tetris, which basically shows with this clever ordering, what we can do in our approaches is in the orange and in the blue, we're able to improve relative to the prior best work on these different benchmark molecules, decreasing the cost, right? The cost here is the number of 2-qubit gates you need to execute. In near-term quantum computing, these 2-qubit gates are considered to be the primary cost. We always try to compile to decrease 2-qubit gate costs. The typical 2-qubit gate is the CNOT gate. All of this is nice, right? So we're able to optimize on, the primary cost here. But if you look at this, there's kind of a secret. The secret here is if you try to run this circuit on any kind of realistic near-term quantum computer, even just a subset of these blocks, right? Say that you take 10 out of hundreds of these poly strings and you execute them on realistic hardware, what you get is the overall accuracy of the execution quickly decays to 0, right? The problem is NISQ, so near-term quantum hardware, is too noisy, too inaccurate to run quantum chemistry problems bare metal without any error correction. And while it's nice that we optimized on this goal, this cost, the realistic execution put into real hardware makes it so that this is not a candidate for real useful quantum computing. So I want to teach you about the evolution of the field to the next idea, and then I'll take some more questions. So the next evolution here in this field is that people try to make ansatzes that are not as deep, so not as many gates, not as many blocks, and not as difficult to execute in the hardware, by this idea of let's try to construct the ansatzes one stage at a time, and at each stage, try to optimize so that that ansatz is trainable, such that it's a good ansatz, a good imitation of the real quantum mechanical dynamics of the molecule, without necessarily paying too much attention about the polystrings themselves. This approach, originating in a paper called Adapt VQE, and then subsequently there have been more generations of this approach. The Adapt VQE approach in this diagram here looks like this. The idea is you come up with a pool, a collection of trial operators. So these are little widgets that you can attach to your ansatz. At any given stage in the quantum computer execution, you look at each of these operators in the pool and you say, if I attach this operator, does this make my ansatz more trainable? And if so, what is the gradient of the resulting ansatz? At each stage of the execution, you select from them the best operator. you put it onto your quantum circuit. So this is now my ansatz. You snap new stages to the ansatz. You train it as before, and you iterate the overall loop, adding more and more ansatz layers until you see that each new layer is no longer contributing a better estimate of the ground state energy underneath some threshold. Again, this diagram is an illustration of the original AdaptVQE paper by work done by Xiongwu in this year, depicting this approach. And this seems to be very nice, right? So this approach, if you take the AdaptVQE approach and you go look at all the papers from physics describing the AdaptVQE approach, they have excellent results, right? So what they do is they evaluate those ansatzes, the adaptive ansatzes, in a noise-free strategy. And assuming this perfect idealized quantum hardware, they can keep attaching more and more stages and more layers to the ansatz and essentially achieve nearly arbitrarily low error versus the true ground state energy, far more precise and more accurate than the threshold that we established called quantum chemical accuracy. Right? All of this is very nice. The theory of the ansatzes, the adapt ansatzes, is excellent. But the moment that you take those ansatzes and you add realistic considerations about mapping the ansatzes to the hardware and evaluating the ansatzes with noise in the hardware, what you realize is none of these ansatzes ever approach chemical accuracy, right? The theory of adapt ansatzes, adapt BQE ansatzes, does not take into consideration realistic hardware constraints and realistic hardware noise. Right, so what I've talked about now is we're working toward this goal. The first couple generations of ansatzes first was accurate, was true to the chemical form. Then the adapt approach kind of sidesteps that and makes trainable networks. But neither of those directly take us to the level of useful quantum chemistry, which is accuracy within this particular figure here. And so my next couple stages that I'll try to show, kind of key points, is what are alternative approaches to reach that level of accuracy. Okay, so I'll take another pause here. Happy to take questions. We're right now here about to talk about hardware efficient ansatzes.
Can I ask question?
So Malik, an issue is your audio is a little bit choppy. I think that there's some bitrate problem. Would you mind typing your question into the chat box and then I can take a look? But yeah, otherwise I'm happy to take questions either live or via the chat interface. Okay, so our next stage of the talk today, the next stage of this tutorial is what does it mean to take an ansatz and make it efficient versus hardware, bare metal hardware, and can you combine the hardware efficient approach with the gradient maximizing adapt approach? And once you do that, how close does that take us to useful QC without error correction? And our response to that is that takes you to a level where you still need 1000x improvement in accuracy. The observation here is that if you take your gradient maximizing adaptive ansatzes and map them to realistic quantum hardware, say superconducting qubits, the qubits have different connectivity constraints. So ideally, you want a graph where every qubit can talk to any other qubit. This is called all-to-all connectivity. But realistic quantum hardware has fairly sparse connectivity between qubits and qubits. And as you take your ansatzes and try to map them onto the hardware constraints, what happens is your cost of routing the circuit incurs 2-qubit gates, those 2-qubit gates thereby increase the total number of gates you need, and they also increase the depth of the circuit, so how long the circuit is. As the topology becomes sparser and sparser, the overheads from mapping and routing increase relative to the idealized all-to-all connectivity. And so what happens here is that once you perform this mapping, the candidate ansatz choices, right? So each of these dots now are candidate operators in the pool of operators that adaptive VQE can choose from. Every one of those candidates has some score in terms of the change in the gradient of adding that layer to the ansatz. And the original adaptive approach will always try to maximize the gradient, right? This is called gradient maximizing, right? So it will choose the very best gradient maximizing ansatz layer. The consideration here is, well, those candidates, they also have a cost, right? They have a cost in terms of the number of 2-qubit gates they add to the ansatz cost. And so if you consider the benefit and the cost, then the valid choice is no longer just one, but rather there is a continuous trade-off between benefit and cost. This is called in economics a Pareto frontier, where each of these candidates are ones where they either increase the benefit or decrease cost. And choosing among any of these candidates is a valid choice if you are trying to both maximizing gradient while minimizing cost, right? So this is basically the whole key idea. We want to make choices that evaluate both. And so how useful is this, right? So if you're able to consider both the cost benefit of any given ansatz choice, then what we arrive at is if you perform the adapt VQE approach without considering the 2-qubit cost, then roughly speaking, the hardware needs to be about 1,000 times more accurate than it is now to even approach chemical accuracy, right? So this plot here is plotting in the idealized black line quantum computer execution without mapping and routing constraints and without any noise. The process of adaptive QE adds layers to the ansatz, and each layer improves the ansatz's ability to approximate the ground state. And the adaptive approach without noise is able to beat chemical accuracy no problem. But as you add realistic noise, then none of them approach chemical accuracy consistently. But if you're able to trade off both cost and benefit of any ansatz choice, explore that Pareto frontier, then even hardware that is just about 1,000 times more accurate than models of current hardware, they are able to just break that threshold, right? They're able to just break that threshold that we call chemical accuracy. All right, so this is, if you ask me, what's a summary figure of how far does this Q hardware have to go for this benchmark, I would say that the error rate needs to improve by 1,000x. Okay, so I'll pause here, right? So this is the unit talking about hardware efficient ansatzes. I'll pause to take questions here. I see there's a question in the chat. So Malik's question, is there any trade-off or caveat while choosing code-efficient ansatz? Or is there caveat to code-efficient ansatz? Right, so your question is about code-efficient ansatzes, which we haven't gotten to yet. All right, so far I've told you about NISQ era hardware. The notion of this novel idea of code-efficient ansatzes is our next step. A few more seconds for any potential questions here. Let's take a break. We're right now here.
Sorry, am I clear in my voice now?
Yeah, your audio is much better now.
Yeah, I was asking, I mean, if we have to choose this code efficient ansatz, so you were saying we need 1,000 times more efficient hardware as well, or accurate hardware as well, which is right now. Am I right?
Yeah, so I think your question is about if we choose code-efficient ansatzes, like what is the improvement in accuracy of the hardware that is needed? And the notion of what a code does, so what a quantum error correction code does, is it provides that 1000x improvement in accuracy. The idea is that you can now team up hardware qubits that are themselves as inaccurate as the hardware that you have now, but by using a raw number more of such physical qubits, we're able to arbitrarily improve the accuracy of the resulting code. And if you look at the roadmaps for IBM and Google, and the general vision for quantum computing, this is the long-range goal. The long-range goal is we want to use thousands to millions of physical qubits, which are themselves not any more significantly more accurate than they are now, but be able to construct codes, specifically surface codes, to build fully fault tolerant, so FTQC, fully FTQC. This requires thousands of physical qubits for a single idealized logical qubit. And this is able to push arbitrarily low logical error rates, right? So if you want 1 in 1 million execution accuracy, if you want 1 in 1 billion execution accuracy, all you have to do is have a sheer quantity more raw physical qubits. In these codes, running circuits is tricky, right? So originally in the physical qubits world, in the machine qubits world, you could provide microwave pulses, and those qubits can execute any arbitrary quantum gate. We call this universal quantum computing. But in codes, the codes have a native language. The native language is the gates that can be executed in the code without special treatment. And in surface code specifically, a very few number of gates is considered native, and there are gates which require extra resources, separate cost, right? So I'd like to tell you about how this works and this consideration. And what that means, if you're looking at a fault-tolerant quantum computer, what does it mean to compile ansatzes that are efficient relative to that type of code? So what I need to tell you now is this idea of universal quantum computing. Right? So universal quantum computing means that for a given qubit, I have access to the full Hilbert space that that qubit can explore. A single qubit we represent in this representation called a block sphere. In the block sphere, they represent the qubit states. You have your classical Cat0, Cat1 states, but you also have the superposition states, so uniform superposition between 0 and 1 with equal mixture. In phase, the Cat plus state is located here. And then you have equal superposition, but 180 degrees out of phase, Cat minus is over here. And then you also have the states that are 90 degrees out of phase in the positive and minus direction. These are the states that we call our stabilized versus the polys, meaning that if you apply these polygates to these particular states, they don't go anywhere, right? So this is called the poly states or polystabilized states. Between the polystabilized states, we have a limited set of gates called Clifford gates. So these Clifford gates include things such as CNOT, Hadamard, and phase, CHP. And these gates, called Clifford gates, have a special property in that they take you between only these special points on the block sphere. So for example, the Hadamard gate, or Hadamard single qubit gate, takes you between 0 and ket plus, ket minus, and ket 1, right? So it's a kind of 90-degree, it's kind of rotation about a specific axis that performs this transformation. And then another type of gate called the phase gate. This is represented as either capital S or capital P. This type of gate, in the red arrows, are a 90-degree rotation around the z-axis. So you go from ket plus to ket plus I to ket minus I in the back and ket minus I over there. Um, these gates, CHP, C0 Hadamard phase, don't take you to the full surface of the Bloch sphere. And we can now create a map of these types of gates in increasing complexity or an increasing ability to fully explore the Bloch sphere. And this is called the Clifford hierarchy. The Clifford hierarchy looks like this. So the Clifford hierarchy, you have in the bottom level of the hierarchy, identity. First level of Clifford hierarchy, you have your poly-stabilized states. So Z is a poly, so is X, so is Y. Second level of the Clifford hierarchy, you have the gates that take you between the poly-stabilized states. Right? It takes you between those 6 special places on the Bloch sphere. We have our phase, also called the S gate as before. And you also have gates such as C0, which is equivalent to a control Z. So up to here, everything below Clifford hierarchy level 2 is uninteresting. It is not powerful. It is no more powerful than classical computing. What you need is, at the very minimum, a single non-Clifford gate that allows you to perform now a 45-degree rotation that now frees up the Bloch sphere for you to fully explore its Hilbert space. A minimum example of such a Clifford hierarchy level 3 gate is the T gate. It's a rotation about the z-axis by 45 degrees. If you have access to a T gate, then you have universal quantum computing. And so this is the consideration for FTQC in this setting. We can consider the availability of T gates in the form of magic states to be now the primary cause of this form of quantum computing. So where before C0 gates were the expensive part of MISQ execution in FTQC, the availability of T gates is the cost. And the reason that this is impactful on how you construct ansatzes is these T gates, these 45-degree rotations about the z-axis, consume these things called magic states. So magic states are a resource state, which is a qubit that has been put on a special point on the Bloch sphere. So I have my Bloch sphere here as before, but between the 6 special points on the Bloch sphere in this geometry, there are different types of magic states that are not stabilized. And what you can do is you can consume these magic states to synthesize any rotation that you want, right? So suppose I want a rotation to a qubit state that points off in some strange direction, you can use two algorithms. One is called Solovay-Kitaev, which is older, and a newer one called GridSynth, which consumes magic states to interpolate your state until it points into any arbitrary location in the block sphere. And so now there's this new trade-off, depending on how accurate you want your approximation to be. So here, very inaccurate. Over here, highly accurate, highly precise. These incur T magic states. And so the more accurate you want to reach a given point, you need to use more gates to get there. And this plot here comes from students taking my graduate course right now, CS558, Quantum Computing Programs and Systems. This year, these two students, they are working on a project implementing GridSynth and showing exactly what is the separation between the cost. Right, so as you see, GridSynth is more efficient than Solovay-Kitaev, but still, it has a cost in terms of reaching precision. And given this, we now have a new frontier to explore. Right? So whereas before you had several valid choices of ansatzes with respect to the number of CNOT gates, now if you want a highly precise ansatz layer, operator pool ansatz layer for the adapt approach, conventionally, the original adapt VQE approach will always try to synthesize those rotation angles as precisely as possible. But if you are trying to cut down on the number of T gates that consumes, then there is a whole frontier of optimal points, which minimize the number of T magic states that layer will consume. And so now, again, there is a valid trade-off between the benefit of optimizing gradient maximizing, and T-gate minimization. This is, once again, impactful for the execution of gradient maximizing ansatzes in FTQC hardware. So in a code-efficient way, this means that you can explore different choices of the precision that you would like to synthesize ansatz rotations to, right? So you can go at 1 in 10 accuracy in your state approximation, an epsilon of 0.1 is over here. So in this very poor accuracy, poor precision compilation, synthesis of those angles, what you have is the energy error, right? So how accurately you're estimating the ground state energy. If you did not have to account for T-gate costs, the original adaptive approach has no problem. It easily, handily reaches higher levels of precision as you add ansatz layers. But because we're approximating the angles with such poor precision, then that introduces a kind of synthesis error, error in the synthesis angles, such that GridSynth plus adaptive cannot approximate the true ground state energy. And likewise, we can look at the other extreme case, which is that we approximate angles extremely precisely, right? So we use epsilon of 1 in 10 to the negative 5, so not even this point here, but somewhere out here, it has some further cost in gates needed to reach that level of precision. Then relative to adaptive VQE, without considering this cost, well, if you are consuming that many T gates, the T gates, the magic states themselves introduce a little bit of distillation error, like error intrinsic to how good the resource state is, and or waiting for all those T gates to be available. So waiting for the T gates to be available incurs a cost in the form of a deeper circuit, right? The bottleneck of FTQC is the availability of T magic states. The longer you wait for T magic states to be available, your logical error rate suffers. And that also makes it uh, not as accurate and precise compared to the naive case. And there's some middle ground. There's some middle ground of an appropriate choice of epsilon, of the precision that you're trying to estimate a given rotation angle to be, such that the sources of these two errors are both minimized, right? This is kind of the adaptive BQE approach in a fault-tolerant quantum computing setting where the realistic costs of executing the ansatzes and their rotations in the surface code is fully taken into account. Okay, so I'll pause here once again to take questions, and also I can field questions in the chat.